Okay, good morning, and thanks to those of you who showed up today. I'm sorry I couldn't teach yesterday, but I didn't want to completely miss this lecture, so that I thought we could then. Anyway, it's only a recap, mainly a recap of Deutsch and also the extension, which is Deutsch-Jozsa. So that's what I wanted to talk about today. So let's recall by stating the problem first. So given a single bit Boolean function, so x is just either 0 or 1, it's single bit, is f of x constant or balanced? That's the question. Constant would imply that f of 0 is equal to f of 1, and balanced would mean that f of 0 is not equal to f of 1. Balanced just means that the output is equally 0 or 1, right? So the output also, so remember that the output is also just 0 or 1, right? So constant just means that you get the same output, which is either 0 or 1. Balance means you get both outputs, right? And for a single bit Boolean function, these are the only two possibilities. So in that case, it's a sort of well-posed problem, okay? And what the Deutsch algorithm says is, let's solve this using the oracle model. So you're given a quantum oracle, right? Which, if you recall, is basically a unitary matrix. So just like how in the classical case, you would imagine that you have a black box f of x. So let me just quickly describe the classical oracle. So the classical oracle is just a black box that implements f of x. And then you have to, if you input 0, it gives out f of 0. If you input 1, it gives f of 1. Then you compare the two, and then you say whether f of 0 is equal to f of 1 or not. How do you compare? So when you compare the outputs, what is the function you use? It's an XOR, right? Because if f of 0 XOR f of 1, so write it out. So the input is x, the output is f of x. And why is the XOR function useful here? Because so what does the XOR function do in terms of comparing whether f of 0 is equal to f of 1 or not? Basically, this is 0 if, yeah, so what happens if the XOR output is 0?
Both functions are the same.
Yeah, so this is constant and this is balanced, right? So I hope you see this. Okay, so yeah, this is what I wanted. Just give me a second. Yeah, so it's 0 only when f of 0 is equal to f of 1, and it is 1 when f of 0 is not equal to f of 1, right? And this is how classically you can tell whether the function is constant or balanced. You need to do the XOR of f of 0 and f of 1, and this you can do only in a serial fashion, right? So in order to do this, you can only do this in a serial fashion. Given a single oracle which computes the function f for you, you input 0, you get the output, you input 1, you get the output. So in a sense, you get to know f of 0 and f of 1, and then the XOR of the two functions will tell you the answer, right? So now Deutsch proposed this quantum oracle, right, which is now a unitary function a unitary operator or a unitary matrix, which depends on F, right? Because it has two inputs and two outputs. It's a 2-qubit unitary, right? This is X, you can say, and this is Y. Now that we're talking the language of algorithms, I will say this is the data qubit, okay? Because this is really the qubit which I'm going to probe, use to probe. So this is the qubit, this is like the X here, right? This additional qubit is an ancilla qubit, right? And what this does is it does nothing to the first qubit or the data qubit. That simply comes out as it is, right? And what it does to the second qubit, it computes the XOR of Y with f of x, right? So this gives me Y XOR f of x. Okay. So if I were to describe the action of this oracle, this is xy, this is equal to x, y XOR fx. Okay. Now, by giving different inputs to this, we can try to understand the function of this oracle better. Okay. So what I would like to do is basically to extract out the property of the oracle itself, like what exactly is the oracle doing, right? So let us say that x is 0 and y is the superposition state 0 minus 1 by root 2, right? So then what happens? Uf 0 minus, right, gives me 0, 0 XOR f of 0 minus 0, 1 XOR f of 0, right, by root 2. Now, depending on what f of 0 is, you can see that the state takes on two different, this can be two different states, right? So now if f of 0 is 0, so let me call this state something. So let me call this psi, okay? And then we'll say that if f of 0 is 0, then the state psi becomes what? 0, 0 minus 0, 1 by root 2. So essentially it becomes 0 minus again, right? And I will write this as minus 1 to the 0, okay? 0 minus, okay? And if f of 0 is 1, then psi becomes 0, 1 minus 0, 0, right? So then this is nothing but 0 minus, but with an overall minus sign, right? So this I will say is minus 1 to the 1, 0 minus, okay? So if I were to abstract this out now, then UF acting on 0 minus is basically minus 1 to the f of 0, 0 minus. I hope you see this, and it's up to you to now check that UF acting on 1 minus will have the same property, that it is minus 1 to the f of 1, 1 minus. Okay? So this really is what the oracle is achieving. It is taking UF x minus to minus 1 to the f of x, x minus. Okay? So this is an alternate way to describe the functionality of the oracle, that it is able to pull out the value of f of x onto a face. But now note that if I were to simply input like this, then this is actually an overall face. And this is not something that I can experimentally get a handle on, right? I cannot really estimate this phase. It's an overall phase. But if I were to now query in superposition, which is if I were to make this X into a superposition state, then this phase becomes a relative phase, and that is how I extract the information out. Right? So I'm just trying to give you an intuition for how the algorithm works, what the oracle is actually doing. So what some people like to do is to simply state the Deutsch oracle as Q as something that takes x to -1 to the f of x, x. Okay? Because this second qubit here is simply an ancillar qubit that's kind of coming in for a ride here, right? So this is an ancillar qubit. But of course, its role is important to achieve this functionality. So in some sense, theoretically, this is the desired functionality of the oracle. Because from the classical intuition, we know that we need to compare f of 0 and f of 1. And if you want a quantum speed up, then the way to compare this would actually be to interfere two phases. And that can happen in a parallel way, right? And that's what is going to give you an advantage. So this is the desired functionality of the oracle, but the way to achieve it is via such a unitary. And this is the implementation of this. And for that, you need this oracle, and you need, you need this ancilla. And what is more, you need this ancilla to be in a superposition, which is the minus state. Okay? So please understand this functionality. If there's anything unclear about this, let me know. Because now the Deutsch algorithm is very easily described. So now, once you have this, so I will call this as equation O, because this is the key oracle equation that I need, right? So equation O essentially describes the quantum oracle. The reason I'm stressing on this is because we will essentially require a very similar functionality for the Grover search algorithm also. So this kind of a thing where the oracle picks out some property of the state and casts it into a phase is called marking, right? So in the search algorithm, what we will need to do is to mark the correct outcome of the search. And the way to do it again will be to take this information out in a phase, and then you interfere these phases and you get the speed up, right? Okay, so equation O describes the quantum oracle, but now I'm going to query via superposition. So these are the two aspects of the Deutsch algorithm which give it the speed up. So which means that my x is now going to become the plus state, right? And then you will see that UF acting on plus minus is UF acting on 0 minus plus 1 minus. And this, you know, now gives me an overall 1 over root 2 minus 1 to the f of 0, 0 minus 1 to the f of 1, 1 minus right? And so I can now write this as an overall, yeah. So basically now you see that this gets you two options. There's an overall -1 that I can pull out. And then if f of 0 is equal to f of 1, then what do I have in the first qubit? So it becomes plus or minus and then minus. And this one is basically plus if f of 0 is equal to f of 1. And this is minus if f of 0 is not equal to f of 1, right? And that's it. So this tells me whether the function is constant or balanced, right? So what are the steps of the algorithm therefore? So is all this clear? Any questions? Okay, so if I were to give a circuit description of the Deutsch algorithm, so here's the circuit. I have the oracle. Now I must input a plus here, remember. So the way I do it is by preparing my qubit in 0 and then applying a Hadamard. The way I do this is by preparing my qubit in a 1 and then doing a Hadamard, right? This is the X and the Y. And then in what basis must I measure the first qubit? Yes?
0 and 1.
If I measure as such, if I measure, suppose I put a measurement here and I measure in the 0, 1 basis, will that tell me whether the function is constant or balanced? Look at the output state. This is what we have input, right? We have put Hadamards. So what basis should we measure in?
Plus minus, I guess.
Plus minus.
So you have to measure in the plus minus basis. If you measure in the 0, 1 basis, you're not going to get any information out. Half the time you will get a 0 and half the time you will get a 1. That says nothing. So this is wrong. This is not what we need to do. However, if I were to think about implementing this practically, so okay, so the measurement you have to do is actually a plus minus basis measurement, right? But instead of writing it like this, what I'm going to do, suppose my experimental toolkit has only the 0, 1 basis measurement. Then how will I do this measurement? Suppose I don't have the ability, I don't have an experimental setup which is going to measure in the plus minus basis. Then how will I do this?
Harder market again to change the basis.
Very good. Yes. So I need to do a Hadamard and then measure in the 0, 1 basis. So we have to be very careful with the final measurement step, right? You don't want to mess up all the good work you have done by measuring in some wrong basis, right? And completely collapsing the state out without getting information. But this way, I will get information because now if I apply a Hadamard here, this is going to become a 0. If I apply a Hadamard here, this is going to give me a 1. So now I know that if my output is 0, then it's constant. And if my output is 1, it is balanced. And if you notice, this is exactly like computing in the classical case, f of 0 XOR f of 1, right? Just go up, look at this. There you go. If it was 0, the function is constant. If it was 1, the function is balanced, right? So what you have done with all this machinery of this quantum oracle and Hadamards is to essentially realize the same classical functionality, except that now you're doing this in a single shot as opposed to having to query the oracle twice. We don't quite care about what the ancilla does. It is in some state. We don't care what that state is, right? Now, one more thing to mention here is this first step of preparing the qubits, right? This is called the initialization, right? And when we initialize these qubits, we may not again have the machinery. See, when you're building an experimental, toolbox for this, then you don't want to have too many components in the toolbox. So it's possible that you don't have the one preparation directly, but you have only the ability to prepare zeros. Okay, and typically your ancillas, you will start by initializing them to zeros because that is something you can do with high fidelity. Okay, so then how will we get to the 1? So suppose I can only start with the 0, then what do I do?
Bit flip gate, X
Correct.
gate.
So this is one way of describing the complete circuit. All my qubits are initialized to 0, whether it's the data qubit or the ancilla. Then I apply a series of gates so that this becomes a superposition, this becomes another superposition, then comes the oracle, and then this. Okay. Now, one key step which is missing here is really what is the circuit for this oracle? Okay, before that, let me just state that the query complexity is 1 in this case, but classically, this is the quantum query complexity. Classically, this is 2. Okay, so it seems like you have, it seems like you have made it half as hard in complexity. But next we'll see how it's actually an exponential speed up, right? But what about the circuit for this oracle? Now, the circuit for this oracle actually depends on the function in question, right? So depending on what f is, we will have a certain unitary matrix that we will write down. And then we will try to decompose it in terms of the elementary gate set in the architecture. And that's how this circuit gets built. So I cannot a priori give you a circuit for this. That will have to be constructed based on the problem. So if you look at assignment 3, which has been posted, then you will notice that there is a certain Boolean function that I give, but that's actually not just a single bit Boolean function, it's a 3-bit Boolean function. So the first task for you will be to go from this to UF, which is to identify what is this unitary. And then you give it to the IBM composer, right? And that will decompose it for you into a circuit. Okay. So by the way, I haven't given you instructions for assignment 3. There are 2 problems which you have to implement on IBM. I will write out those instructions in a separate sheet and post it on Moodle. Okay. You can basically log in using your SMail ID. I think I already told you this, and there is an IIT classroom that you can pick, and that will give you access to a lot more machines and actually help you run these algorithms. Okay. All right, so this was the single bit Boolean function. Now, what happens when you have an n-bit Boolean function, right? That's what the Deutsch-Jozsa algorithm looks at. So I should say that David Deutsch is a physicist at, I guess, I don't know, Oxford or Cambridge. Jozsa is a computer scientist. And this probably was one of the first true collaborations between a physicist and a computer scientist to come up with an exponential speed up type. So the logic is the same, but some of the details are slightly different. So it's worth discussing this as well. So what the Deutsch-Jozsa algorithm solves is this problem, that now I'm given an n-bit Boolean function, which is basically fx acting on an n-bit string and taking it to a single bit output, right? So the input is an n-bit string, but of course a Boolean function always has a binary output, right? So the output is 0 or 1. And now you are given a promise, okay, that this function is either constant or balanced. Now, like I said, in the 1-bit case, it's a natural property that the function is either constant or balanced. But in the case of the n-bit function, this is actually an artificial constraint that we are imposing, right? Because constant then means that f of x is some c which is either 0 or 1, for all x. And how many x are there in this case? How many possible inputs are there?
2 to the power n.
Yeah, so for all 2 to the n strings. Balanced would mean that f of x is some c1 for half of them, which is therefore 2 to the n minus 1 strings, and it is c2. Now again, c1 and c2 are either 0 or 1 for the remaining such strings, right? Okay, so once again, classically, I have an oracle which now takes, if each of these lines represents a bit, so then there are n bits, right? It takes an n bit input and gives you a single bit output, right? So now how many times do you need to query the oracle? So this is together, this is the x, which is the input. This is f of x. How many times do you need to query the oracle before you can decide whether the function is constant or balanced? Is it 2 to the n?
2 to the n minus 1 plus 1.
Okay, that's 2 to the n by 2 plus 1, right? Because I have to query at least half the strings. Now, even if this entire set of 2 to the n minus 1 strings gave me the same output, I still cannot conclude that it is constant because I could have queried exactly this set of 2 to the n minus 1 strings. So I need the extra query before I can decide whether it is constant or balanced, right? And now what the Deutsch-Jozsa algorithm tells you is that if I have a quantum oracle, then the number of queries is 1. Okay, and so this is the first example of an exponential speedup. Right? So you've gone from something which is scaling. So why is this an exponential speedup? Because this function is scaling exponentially with n. N essentially captures the input size, right? That's the number of bits in the input. In the quantum case, the n will translate, of course, to a 2 to the n dimensional Hilbert space, right? But this is what captures the size of the input. And the speed up is in noting how the algorithm scales, the complexity of the algorithm scales with the input size, right? And in this case, the query complexity is scaling exponentially in the classical case. But in the quantum case, it's actually just a fixed constant, right? So there is a constant number of queries, just that the constant is 1, but actually it doesn't matter. It could have been any other constant also, right? But the contrast is between a constant number of queries and an exponential number of queries. And this contrast is what we call an exponential speedup, right? So how do we achieve this exponential speedup? The construction of the oracle is exactly the same, right? So we use, so let's look at the steps of the Deutsch-Jozsa algorithm. So we use the same oracle. which means it's an oracle that is essentially going to have this -1 to the f of x, extract the phase information out, right? But now the x is an n-bit string. So what this UF is going to do is it's going to have this. This is now, how many qubits do I have here? So this is an n-qubit input, okay? Because I need to have a way of computing f of x for all 2 to the n classical bit strings, right? Which means in the quantum case, this translates to having 2 to the n orthogonal quantum states. And for that, I then obviously need an n-qubit register. This is often called a register in this computing language, right? So just like how in the classical case, my oracle input was an n-bit register, now my input is an n-qubit register, but I need one additional qubit, right? So I need this additional qubit, which is my ancilla qubit. Once again, if I were to think of this entire set of n qubit state, I'm going to call this as x. Okay, the x now, so let me just state this here. X belongs to C2 tensor n. In other words, it's an n qubit state. Okay, and I'm putting individual lines for each qubit, but this entire state is what ket x is, the state of this set of n qubits. The ancilla is a single qubit state. Okay. The output is again the x, which is an n qubit state. Nothing happens to the set of the data qubits remain ket x itself. That's the functionality of the oracle, right? And this outputs y XOR f of x. Now, once again, so remember that all that we've done now is to scale up the oracle, the quantum gate, from being a 2-qubit gate to what is the dimensionality of this gate? It's a gate on n plus 1 qubits, right? I've just scaled it up to achieve the same functionality. So once again, all the arguments will go through. So now if I input some x minus, where x again, remember, is an n-bit string. So ket x is actually, well, it's a state in the 2 to the n-dimensional space, right? Which means it's a state on the n-qubit space, right? So this is again an n-qubit state. This is going to again give me -1 to the f of x, x minus. Because that mathematics just hasn't changed. That's just the same. There's just this is what it is, right? Okay, before the superposition. So here. Now it doesn't matter whether what was here was a single qubit state or an n-qubit state. This functionality remains the same, because this is going to follow exactly the same thing. This state remains unchanged. Instead of a single ket 0, it's going to be 0 tensor 0 tensor 0 n times. Instead of a single, yeah, and so on and so forth. So for every state, you can work this out, right? And you will see that this follows exactly the same thing, because this f of x is sitting here, right? So if you wish, I can rewrite the steps again, but it's the same thing. You just put an x instead of 0, and that x can be of whatever dimension, right? You just have to find the u of appropriate dimension. That's all. Okay, so this functionality is the same, right? So it's the same quantum oracle. And so now the next step is to query in superposition, right? We've constructed the oracle. Now we need a superposed input so that we can query in superposition. And that's why it's a fixed number of queries. It's just one query, because we are going to make a uniform superposition of all the 2 to the n orthonormal states that form the standard basis or the computational basis for the n-qubit space. So uniform superposition of all the basis states of the n-qubit space. So what does that mean? So the n-qubit space is basically, like I said, it's C2 tensor n, right? C2 tensor C2 tensor C2, etc. n times. So the orthonormal basis for this, what we call the standard or computational basis, has states of the form all 0, right? And there is n of them. This is an n-bit 0 string. You see, the labels of these computational basis states are all the classical bit strings, right? That's the basis that we call the standard or the computational basis. So all zeros and 1 1, all zeros and 2 1s, right? Rather all 0 and 1 0, all zeros and 2 1s, etc., etc., until you hit the all 1 state, right? This is the n-bit 1 string. So I hope the basis is clear. So then the question becomes, how do we get this superposition? How can we make this superposition state? So what is the state I want to make? I want to make a state, let me call this some phi, already used psi for something else today, which is sum over all x belonging to, so this is the notation that I'm going to use, sum over all x, where x is an n-bit string. The way you write this formally is to put a cross n here, right? So x belongs to the set of all n-bit strings, ket x, but this sum is not normalized, right? So what do I need outside? How do I normalize this?
1 upon under root of 2 to the power n.
1 over 2 to the power n?
No.
Square root.
Okay, good. Yes. Now, how do I get to this state? So the question is, suppose I start with the all 0 string. That is, you can call it 0 tensor n, which is the same as all zeros. Okay. How do I get to this? So this is clearly the uniform superposition state, right? So how do I go from this to that? It's just an extension of the single qubit case, right?
N-bit Hadamard.
Exactly. Didn't you guys do a problem about this? So there was a question in assignment 2, right? It said something about the n-qubit Hadamard. What did you guys show in that question? you showed that when you have an outer product notation for the n-qubit Hadamard, then that involves all n-bit strings, correct? Yes, no? Is that a distant memory of the past? Wasn't that the question? Okay. Looks like you've all decohered much faster than quantum memories now. Huh? I thought you just submitted the assignment last weekend. Okay, maybe a little bit before last weekend. Anyway, so yeah, the way to do this, so these are indeed the steps of the algorithm now. So apply H tensor n. So then this is Hadamard tensor n on the all zero state, gives us the state phi, which is a uniform superposition. X belongs to 0, 1 cross n, x. Okay. So this is the first part of the circuit done, right? I have UF. I have this n-bit string. So I'm going to write here that this is simply Hadamard tensor n. So you see, this Hadamard tensor n is very easy to implement because it is simply Hadamard on each individual qubit, like this, right? That is what H tensor n is. There's nothing correlated happening out here, right? And these are all, the inputs are all zeros now. There are n qubits here. This is the ancillary qubit. Same thing. I start with a 1. Instead, I'll say that I start with a 0 and I put an x. The key question is the measurement. So how are we going to measure? We have n qubits. So there are 2 to the n possible outcomes, right? We have, I mean, how do we assign now? How do we map the output to the answer, whether the function is constant or balanced? So that's the last part that we need to do. So to do this, it's useful to write down what the Hadamard is doing. Actually, yeah. So at this stage, you know what the output is. So let me just, okay, so let me complete this for you and then we'll analyze this so that in case I run out of time today, we can continue this next time. So I hope it should be clear that we again need to do a Hadamard here, okay? And then measure all of them in the standard basis, right? So each qubit gets measured in the standard basis. So note that whenever I put this measurement symbol, it always refers to the standard basis unless I actually state otherwise, right? So like I said, we always try to initialize qubits to 0 as far as these algorithms are concerned. We always try to measure in the 0-1 basis. So what has been input is now in the rotated basis, right? Because you have rotated to a uniform superposition of all the computational basis states. So you will probably have to undo the rotation, and that is what this Hadamard is doing here, right? It is again like going from 0 to the plus basis and then back from plus to the 0 basis, right? Except it's not plus, but it is the n-qubit version of the plus state, right? Because it's a uniform superposition with all relative phases being plus, right? Okay, so how does this work? So let's see what is the state here. Yeah, maybe I should indeed resume. We call this some get psi, and I'll probably stop in a couple of minutes and then continue on Monday. So this get psi is basically what now there's a 1 over square root 2 to the n. there's a sum over all x, right? And we said this is what the oracle does. It does x and minus, right? So now the question is, what is Hadamard tensor n on this side do? Or how does that help us, right? So we'll have to understand this. One way to understand this is probably by going to the single bit case. Okay, so suppose I had a, or we can try to do it with some example strings, but I'm just wondering whether I should continue now on it. Okay, so let me stop here for today. I don't want to keep you guys for longer today. So let's resume this on Monday, but think about this, right? How do we solve this? Like what happens after doing this N-qubit Hadamard? So this will work out on Monday. I'll just complete by saying that it turns out again that, see, because I have now 2 to the n possible outcomes, the question becomes, do I really need to measure multiple times? Which means I will have to query multiple times, measure multiple times to get the answer. But that's not the case. It turns out that once you do this n-qubit measurement, so let me say this is the final step, that once you do the n-qubit measurement, you could either get the all zero string, right? Or you could get one of the other n minus 1 strings, which will have one or more ones, right? So this is the all zero string. And this is the, these are the other n minus 1 strings. Okay. So if you get the all zero string, by now you should tell me the answer. What happens? Is the function constant or balanced?
Constant.
That would be the correct guess. And if you get any of the other strings, then it is balanced. So, oops. I hope the constant part should be easy to understand if you think about doing the XOR of all the inputs, right? So somehow you have to now interfere these phases, right? That's what this H tensor n is doing, right? It's going to give you a state which has the sum of these different phases, right? And that will then tell you whether you get the all zero string or a string with one of the ones. And if you get one of these, then it's balanced. And if you get the all zero string, then it is constant. But we have to complete this discussion, and we'll do that on Monday, where I'll then expand this out, right? And we'll try to understand how it happens that it's constant, it's all zero, and if it's balanced, if it's balanced, it is not the all zero string. It is one of the other strings, right? So I hope the logic is clear, and let us stop here. Any questions? Okay, so I'll see you all on Monday then.